Okay, today we're going to be talking about continuity, and essentially we are going to try to figure out a definition for continuity, how to determine whether a function is continuous at certain points. So example 1 is a pretty easy example. Find the points at which the function f is continuous and the points where it is discontinuous. So why don't we start with saying that it is discontinuous at x equals 1 because there's a jump, and at x equals 2 because there is another jump right here. So that means by default that it is continuous at 0 to 1 parenthesis. We want to include 0 because there is a closed dot right here, and we don't want to include 1 because that's one of our points of discontinuity. So 0 to 1 in union with 1 to 2, and then in union with 2 to 4, and for the same reason we want to include 4 with a bracket. So that's just a basic idea of how to look at a graph and determine whether the graph has points of discontinuity or not. Okay, now we have before us the official definition of continuity at a point. So let's say we're looking at a graph, and I'm going to give you two scenarios. Say the first one is over here and the second one is over here. And let's say this first graph looks something like this. And we have let's say a point up there. And maybe we'll call this 2, we'll call this 3, and we'll call this 5. All right, if I said what is the limit as x approaches 2, well, if you track it from this side or this side, it looks like the y value is heading towards 3. So f of x is heading towards 3. Really, we use an equal sign here, but that's really misleading, as x is heading towards 2, y is heading towards 3. But if I said what is f of 2, then you would say it's 5 because that's where the dot is. Now, anytime the limit as x approaches a number does not equal the actual value of the function at that number, hence 3 does not equal 5, then you would clearly say that it is not continuous. Now over here, let's look at a different example. Let's say we have that closed in. Let's say this is the point 2 and this is 3. Well, if I said what is the limit as x approaches 2 of f of x, you would say, well, from this direction it's heading towards 3, and from this direction it's heading towards 3, so we'd say 3. But then if I said, what is f of 2, you'd say, well, it's 3, because when x is 2, y is 3. These two numbers equal each other, so when the limit, so let's look at it this way, when the limit as x approaches a certain number of f of x is equal to that function's value, then we say that it is continuous at point C. So that's a pretty easy definition. And if you're looking to see if it's continuous at an endpoint, you simply take the limit from the right or from the left, because if it's an endpoint, it doesn't have a limit from the other side, and you compare it to what the function value is at that endpoint. So let's apply that to example 2. Find the points of continuity and discontinuity for the greatest integer function. All right, so the greatest integer function, you may or may not know, but it looks kind of like this right here, where you have a bunch of lines, and you have open circles. All right, so you have essentially an open circle and then a closed circle, open circle, then a closed circle, and it goes on forever here. So it's going to be another line like that, another line like that, another line like that, and let's just go ahead and put open here, closed here, open here, closed here, open here, closed here. So you can see that it's a step function is basically what it is. And this function is it's actually discontinuous at every integer value. So what you'll say is this is discontinuous for all integers. And I'm not sure if there's another way to write that. And you'll say that it is continuous from, I guess you could say, negative infinity to infinity, x not equaling integers. I think that's a decent way of writing it. I think they should accept that. So it's continuous, no problem, but it's not continuous at the integer values. All right, now we have the official definition of a continuous function. This can be a little tricky to understand. A lot of students get hung up on this. But a function is continuous on an interval if and only if it is continuous on every point in the interval. A continuous function is one that is continuous at every point, and here is the key right here, of its domain. There it is. In other words, you have to look at what the function is doing at all points that are in its domain and ask yourself the question, is the function continuous for every point in its domain? And if it is, then that means it is classified as a continuous function, even though it may have a point of discontinuity. So that's where it gets confusing. Let's see if we can use example 3a. Let's see if we can use this as an example here. So we have 1 over x. So we know that that looks like this. Now, the first thing we recognize is that x cannot be equal to 0. So x equals 0 is not in the domain of this function. So the question you have to ask is, with exception to x equals 0, is this a continuous function? Am I able to draw without picking up my pencil? Yes, I am, except at 0. So this would be considered a continuous function on its domain. But there is a point of discontinuity at x equals 0. Very confusing. There's a point of discontinuity at x equals 0, but according to this definition, it is a continuous function because the only point that it's discontinuous is a point that's not in its domain. All right, so let's try this and apply this to letter B. We're going to factor the top and bottom. When we do, just the top, so you get x plus 1 and x minus 1, and then x minus 1. So we can see that the x minus 1s are going to cancel. And we know by now that anytime you have a factor that cancels, it creates a hole. So we'll say there's a hole at x equals 1. And so if there's a hole at x equals 1, we can plug that in to the existing function after the factors have canceled, and you get 2. So there's a hole at 1, 2. So if I were to sketch this function, there would be a hole right there, and then be a linear function everywhere else. So is this a continuous function? Well, it is, because the only place where there's a discontinuity is at a point that is not in the domain. X cannot equal 1. So 1 is not even in the domain. So if that's the only place where there's a point of discontinuity, the function is considered a continuous function. All right, so let's apply that same idea to letter C. So we have a linear function when x is less than or equal to 0. So linear function. And maybe I'll draw this in yellow here so we can make sure that we see it well. And then we have a parabola for all x is greater than 0. Now, notice that when I plug 0 in here and 0 in here, I get the same y value of 1. That shows you that this piecewise function is continuous, or they connect with one another at 0, 1. So that makes it pretty clear to see that this is a continuous function. There's no jumps, there's no holes, there's no vertical asymptotes, so it is a continuous function all the way. No points of discontinuity. All right, here's one that a lot of students may or may not immediately recognize the shape of this. If you have x squared plus y squared equals r squared, that is the formula for a circle. And so if you solve this for y, you get y squared equals r squared minus x squared. And then you take the square root, you get plus or minus root r squared minus x squared. Now that gives you an upper semicircle and a lower semicircle. So in this problem, we're only looking at the upper semicircle. So this is going to be a semicircle with a radius of 1. And so we can see that it is continuous from -1 to 1. So this is a continuous function. And that is the idea of the definition of a continuous function. Okay, we're going to switch gears and talk about the intermediate value theorem for continuous functions. And this is one of the main theorems that we're going to learn in calculus. And this is a pretty basic theorem. Basically what it's saying is that if you have some closed interval, bracket a to b, and you have a continuous function, then there must be some value of k. There's a value of k that is somewhere between f of a and f of b, or the y value that you get when you plug in a and the y value you get when you plug in b, such that there's some value of c, which is between x equals a and x equals b, that if I plug c into the equation, I should definitely get a k. So basically, if I could draw out a visual representation of what the intermediate value theorem says, it would say, let's say we have the letter A right there, and we have the letter B right there. Let's say we have f of A here and f of B here. I'm running out of space. There is some C value. Maybe I'll put that in red. There's some value of C. Let's say we have the function that looks like this. There's some value of C that I could plug into this equation, and it would give me a matching K value. And K would be somewhere between f of B and f of A. It's pretty much a common sense theorem. Here's the idea. Let me give you two scenarios. Let's say I am 5'5" today, and next year I am 5'10". Well, there must be a time between this year and next year that I was 5'8". Because the way growth works, it's a continuous function. You don't skip growth. You have to go through all the heights between 5'5" and 5'10" to get from 5'5" to 5'10". So there must be a time. Let's give you another example. Let's say I'm speeding on the freeway. I'm going 60 miles per hour, and I slow down to 40 miles per hour. There has to be a time where I was going 50 miles per hour. Because the way speed works, it's a continuous function. So this is the idea of the intermediate value theorem. And this is what's called an existence theorem, meaning it doesn't tell you how to find the time that I was 5'8" or the time that I was going 50 miles per hour. It just tells you that there is a time that exists that I was going that fast or growing at that particular height. So let's see if we can use this example. You see, we can use this intermediate value theorem to do example 4. So this problem says, is there any real number exactly 1 less than its cube? Use the intermediate value theorem to determine if this statement is true. So the first thing you want to do is you want to take this sentence and write an equation that represents this sentence. So is there any real numbers? So we'll call that x. That is exactly equal to, it doesn't say equal to, but that's implied, 1 less than its cube. So 1 less than its cube, the cube of that number. So the question is this true? Okay, so let's move the x to the other side. So we have x cubed minus x minus 1 equals 0. Question is, does this function equal 0 at some point? Well, let's just say I plug in -2 into my equation. You can do the math later, but you end up getting -7. When you plug in +2, you end up getting 5. Now let's just see what that means on a graph. If I get -7 when I plug in -2, that means I'm down here somewhere. When I plug in 2, I get 5. That means I'm up here somewhere. So that means if this is a continuous function, which it has to be if you're using intermediate value theorem, that means there must be a time when this function hit 0. It can't go from negative numbers to positive numbers without going through 0. So that lets us know that this function has to equal 0 at some point. Now, does the intermediate value theorem tell us how to find the actual x value where this function equals 0? No, it just tells us that something exists, that x exists somewhere out in space. But it doesn't tell us how to do it. And that is the idea of the intermediate value theorem. Let's apply this to example 5. All right, example 5, let f of x equal x squared plus x over x minus 1. Verify that the intermediate value theorem applies to the interval. So maybe I'll put a 1 by that. That's the first goal. Make sure that you can use the intermediate value theorem. And if you can, then find the value of c that is guaranteed by that theorem if f of c equals 6. All right, so we have two things that we need to do here. First thing, let's see. Can we use the intermediate value theorem? Well, let's see if x equals 1 is the only point of discontinuity in this function, and it is, then we don't have to worry about the function being not continuous in this interval because this interval is only going from 2.5 to 4, and 1 is outside this interval. So between 2.5 and 4, the function is continuous. Check. It's a closed interval. It has brackets. So closed interval. Check. So we can use the intermediate value theorem. So let's go ahead and plug in our a. So we need f of a. And that's going to be f of 5 over 2. And for the sake of time, you can do this on your own. I trust that you're able to plug in fractions. You're going to get 35 over 6. And then when you plug in 4, you're going to get 20 over 3. Now this ends up giving you 5 and 5/6. And this ends up giving you 6 and 2/3. So what do we see? We see that f of a is 5 and 5/6. F of b is 6 and 2/3. There must be a time between 2.5 and 4 where the function goes through the y value of 6 because it's a continuous function. It's got to go through 6. So the question now is, how do we find that value? So we're going to set 6 equal to our function and see if we can solve for x. So we're going to cross multiply x squared plus x, 6 times x minus 6. So x squared minus 5x plus 6 equals 0. And we factor that into x minus 3 and x minus 2. Set them both equal to 0. Get x equals 2, x equals 3. Now, which of these two answers applies to our interval, which only goes from 2.5 to 4? It would be clearly that one. So you don't use that one. So x equals 3 would give you a y value of 6, and it is clearly inside our interval. All right, still talking about continuity here. It says find a value for the letter a so that the function f of x, and you have a piecewise function, is continuous. So what do we know about piecewise functions? We know that they have a split point, a point where to the left it looks like a certain function, to the right it looks like another function. And so in order for these functions to be continuous, they have to connect at the point where the two functions split. So they have to have the same y value when the functions split. So when we plug 2 into this linear function here, we get 7. So 2, 7. That means that when we plug 2 into this linear function, we need to get 7 so that the two functions overlap. So 2a plus 1 must equal 7. 2a equals 6, and a equals 3. So that's a pretty easy problem. If a equals 3, then they will both equal 7 when x is 2, which means they will connect, which means the piecewise function is continuous. Okay, here we have this last example. Determine the value of k in order to make the function, here's another piecewise function, continuous for all real numbers. So just so you know, whenever you have one of these situations where h of x is equal to one function if x is not equal to 1, and it's equal to just a number if x equals 1, or something of this nature, this just simply means that the function looks something like this. Means it looks like a particular function for all x's not equal to 1. So it's just a basic function, except it does not look like this at x equals 1. But at x equals 1 and only when x equals 1, the y value is k. So it's some point. Okay, it's not a line, it's just a point. Now the question is, what do we need to make k equal so that we can plug up this and we can make it a continuous function? And that's what we're going to look at here. So let's say we factor x to the fourth minus 1, x squared plus 1, and x squared minus 1, and over x minus 1. Now we can factor this again, and it's going to be x squared plus 1. We can't factor a sum of two squares, but we can factor the difference of two squares. So x plus 1, x minus 1, and then x minus 1. All right, so now we are going to cancel the x minus 1s off. And once again, we know that creates a hole on the graph. And now the question now we have to ask is, what is the y-coordinate of that hole? Well, if we have x equals 1, we're going to plug that into our function that we get after the factors have canceled. So 1 plus 1 is 2, times 2 is 4. Therefore, k equals 4. And if k equals 4, this hole will be patched up, and it will be a nice continuous function for all real numbers. For the sake of time, we will skip example 8. You can look at that on my website if you want to know how to do example 8.